Hi everyone, and welcome back to my flight mechanics class. Today we're going to continue with the longitudinal static stability, and more precisely with the pitching moment due to aerodynamic forces. Aircraft flight is all about balance and equilibrium, and the pitching moment is one of the essential components of this equilibrium. The method used to derive the pitching moment is actually very similar to what was done in the previous lectures with the drag and the lift. We will start by expressing it in terms of its coefficients, expand the coefficients, and derive an expression to find the subcoefficients. So as you can see, the pitching moment coefficient actually depends on the same parameters as the drag coefficient and the lift coefficient, and that is alpha, the angle of attack, IH, the incidence of the horizontal stabilizer, and delta E, the elevator's deflection. So the main aerodynamic contributor to the pitching moment is going to be lift, and what we did in the previous lecture is actually going to turn out to be very useful because we're going to have to compute the contribution of the lift of the tail and the lift of the main wing to the overall aerodynamic pitching moment. And we will do that by multiplying the lift of the main wing times its moment arm with respect to the center of gravity, and the lift of the tail with the moment arm with respect to the center of gravity of the aircraft as well. So again, just like we had said in the previous lecture, if we wanted to be rigorous when computing the vertical component of the lift for the main wing and the tail, we would have to account for the angle of attack alpha and the downwash angle epsilon. And that is if we wanted to be rigorous. So we're dealing with a scalar equation here. So we're interested in the vertical component of the lift of the main wing and of the tail lift. So as you can see, the equation for the total pitching moment due to the aerodynamic forces is going to be equal to MAC, the intrinsic pitching moment of the wing due to its shape or its camber, plus the lift of the wing times the moment arm between the center of gravity of the aircraft and the aerodynamic center of the main wing times cosine of alpha, minus the lift of the tail times the moment arm between the aerodynamic center of the tail and the CG of the aircraft times cosine of alpha minus epsilon. So now the question is, why do we have a plus in front of MAC, a plus in front of the lift for the wing, and a minus in front of the lift for the tail? Does it have to do with the lift being positive or negative? And actually it does not. So MAC for a standard wing with positive camber is actually negative. So that is a negative contribution or a nose down contribution. The plus in front of it is actually simply about adding. The plus in front of the lift of a main wing is actually due to the cross product between the moment arm XCG minus XAC and the lift of the main wing. And we can see here in this matrix, and here we're dealing with a vector operation. So we have only the x components for the moment arm XCG minus XAC, and we have an x component and a z component for the lift of the main wing. So we have L sine of alpha for the x component, and that is positive because its projection on the x-axis is actually on the positive portion of the x-axis. And for the z component, we have minus L cosine of alpha, and we have a minus in front of the lift because the positive portion of the z-axis is actually downward, so lift is negative. So when you compute the determinant, you end up with minus xcg minus xac times minus lift cosine of alpha. So this is only the j component that survives. And because we have two minus signs, they actually cancel out and becomes a positive sign. So you can see that the result is actually exactly what we're getting here for the main wing. And the reason why you have a minus sign in front of a tail lift is because XAC and XCG was swapped. So the moment arm is actually negative, and this is the reason why you have a negative sign in front of it. So the next thing that you need to do is convert that equation into its coefficient form by dividing everything by the dynamic pressure, the reference area S, and the mean wing chord. And this is what you would get. And the next step would be to replace the lift coefficient of the main wing and the lift coefficient of the horizontal tail with the expansions that had been found in the previous lecture, and that is CL0 plus CL alpha alpha for both cases. So this is what you would get. And in this case, we assume the incidence of the main wing to be equal to 0. So alpha of the main wing is equal to alpha. And the book assumes that CL0 of the horizontal stabilizer is equal to 0. And for that reason, it doesn't show up in this equation, and we'll assume that to be true. And as for the angle of attack of the tail, you can see that the alpha tail has been replaced by the expression that we had found in the previous lecture, that is alpha minus epsilon 0 plus d epsilon over d alpha alpha, and this is equal to epsilon, the downwash angle, plus IH, the horizontal stabilizer's incidence, and tau E times delta E, with tau E being the elevator's effectiveness and delta E the elevator's deflection. So now what you need to do is to actually derive the individual subcoefficients that we wanted to find at the beginning. And the method that you're going to use to do that is actually the same method that we used in the previous lectures, and that is to start with this equation and set alpha, IH, and delta E all equal to 0, and that is going to yield CM0. And then for CM alpha, CM IH, and CM delta E, you're going to take the partial derivative of that equation with respect to alpha, with respect to delta E, and with respect to IH. And what you would get is what's on this slide. So this is it for today. And next time we're going to cover the effects of thrust on the pitching moment and what the pitching moment should be in trim. Thank you very much. See you next time.